Next we have number 14, where we have to say to what point or points does this sequence converge, xn, which is 1 divided by n. And here you can understand that n varies over all the positive integers, provided we are using the finite complement topology on R, not the standard topology. Let x be any real number and let U be an open set in R, which is open in the finite complement topology and which also contains x. That means U is a neighborhood of x in the finite complement topology. Now U is an open set in the finite complement topology, which is also non-empty because it contains x, and that's why the complement of U in R is finite. That is why it's called finite complement topology. But then the intersection of this difference with this set is also finite. We have given it a name also. Let's call it F. And what is this set? This is the set of all terms of this sequence. Now as a finite set, this set F can be empty. This is one case, and in this case, no point from this set will belong to this complement. That means every point will belong to U. That is 1 over n will belong to U for all positive integers n. Next, let's assume that F is non-empty, but still finiteness of F is there. So now there will be only finitely many elements in F, or in other words, there will be finitely many points of this type in R difference U. And that is why there exists a largest positive integer n such that 1 divided by n belongs to R difference U. Hence, for higher values of the index n, that means n greater than or equal to capital N plus 1 divided by n will no longer belong to this complement. That means all of them will belong to U. So we see that in both the cases, this one as well as this one, at most finitely many terms of the sequence lie outside U. In this case, all the terms lie inside U, and in this second case, starting from n plus 1 onwards, all the terms lie inside U. At most finitely many terms lie outside U. And that's why our sequence converges to x. But x was any real number, so this sequence simultaneously converges to every real number. This is a very strange thing when you look at it from an analysis point of view. For a topology, this example, you can call it an example, is a very good one. It shows you one extreme where a sequence can converge to all points of the space. But from an analysis point of view, it's the worst type of example. And this is why we do not see this type of topologies in your analytic areas, real analysis, complex analysis, where we stick to only those topologies which are Hausdorff, where sequences, when they are convergent, have only unique limits. And more particularly, actually, those topologies are metrizable. The spaces we work with in analysis, whether it's real analysis or complex analysis, they are all metric spaces. Let's see another one, number 16 next. Consider the 5 topologies on R given in exercise 7 of section 13. We are going to recall when solving the exercise what those topologies were. There are two parts. This is part A. In part A, we have to determine the closure of the set K, the set of all reciprocals of positive integers under each topology. So let's do this first. Before we write the solution, we introduce a notation for our convenience. Those topologies, if you go back and see that exercise, they were named tau I, where I goes from 1 to 5. So if we want to mean the closure of the set K in the topology tau I, we are going to denote it by Ki. Okay, so Ki is the closure of K in the space of real numbers, but with the topology tau I. Tau 1 is the standard topology on R, and for that topology we already know that the closure of K, that is K1, according to this notation, is K union the singleton set 0. In the standard topology, this set has only one limit point, which is this 0. So that will belong to the closure because that's also an adherent point. Adherent point means it's a point in the closure. And at the same time, every point in the set K of course will also be inside the closure. So that's why K1 in this case is this set. The second topology tau 2 is the K topology. You recall that for this topology, the basis consists of all ordinary open intervals in R and also open intervals from which the set K has been removed. Now let's take a point x in R which is in neither K nor is it equal to 0. That means this x is not a reciprocal of some positive integer and x is also not 0. Then one can easily see that there exists an open interval, ordinary open interval, and as such it will belong to tau 2, which contains x but which does not intersect the set K. And at the same time you also notice this basis element which contains 0, minus 1, 1 from which K has been removed, such that obviously this one also does not intersect K because K anyway has been removed from here. And that is why no point which is like this and as well as 0 is a limit point of K in the K topology, that is in tau 2. And that's why K2, that is the closure of K in this topology, is just K. If you still want to see exactly why these things are true, I can show you in one diagram. You look at this diagram. Whenever you see two dashed lines anywhere in any video in this channel, you have to understand that whatever is confined within those two dashed lines is not a part of the solution or proof or whatever we are doing at the time, but is only there for our understanding. Okay, so it's not necessary that you have to draw this diagram in this solution. It's only for your own sake. So this is our real line which say has the K topology tau 2. Now here you can see some points of the set K. 1 is 1 divided by 1, 1 divided by 2, 1 divided by 3, and like that the points go and try to reach 0 as the denominator increases. So all the points, when you collect them, you get the set K. Okay. Now here what we are saying is that x is a real number which is not in K. That means which is not a reciprocal of some positive integer and also which is not 0. So x can lie entirely on this side to the right of 1, or x can lie in between two such points, say here or somewhere else here. X can also lie entirely to that side, to the left of 0. And what we are saying is that no matter where x lies, there exists a sufficiently small open interval like this that will contain x, but that will not intersect K, that won't have any of these reciprocals, which you can easily see. So this is that basis element, the open interval minus 1, 1. We cannot of course show this, that from which the set K has been removed. Those reciprocals of positive integers, they have been removed. Okay. Now because we are in K topology, this is a legitimate basis element which contains 0 of course. If you remove reciprocals of positive integers, 0 is still here, 0 does not get removed. But of course that does not intersect K, and that is why you have found a neighborhood of 0 in the K topology which does not intersect K. So 0 is not going to be a point in the closure of K in this topology. So that's why the closure is only K. The third topology, tau 3, is the finite complement topology. And by exercise 14, the one we solved before this one, K3 will be the entire set of real numbers. That means every point will belong to the closure of K now. Why and how is this exercise helping us? What did we show here? Here we showed that the sequence of reciprocals of positive integers converges to every real number. So if you arbitrarily choose any real number x and choose a neighborhood u, what we did there just now, in the finite complement topology of that real number, what did we show? We showed that almost all the terms of the sequence of reciprocals belongs to that neighborhood. But we only need at least one term. Term means at least one element of the set K to be in the neighborhood for that point to be in the closure of K. But then that just implies that no matter what real number you have chosen, that will belong to the closure of K in the finite complement topology. So that's why K3 is R. Next we have tau 4, the fourth topology, which is the upper limit topology, and that was the topology generated by half open intervals of this type, where it's open on the left side and closed on the right side. That means this type of intervals form a basis for this topology. So here also, just like the second topology, that means the K topology, we take any point x in R which is not in K and also is not 0. Now you will obviously find a basis element of this type now in tau 4 that will contain x and which will not intersect K. Again, you can draw one such diagram to understand why. In fact, it's actually easier to have such intervals than having the other type of intervals that we had in the second topology, that is K topology. Moreover, so that just means what? It means that no such point x will belong to the closure of K in this topology, and additionally, this is a neighborhood in this topology of 0. That also does not intersect K because it's entirely to that side, whereas everything in K is positive, and that is why 0 will also not belong to the closure. So just like K2 is K, K4 is also K. And finally we have the fifth topology, tau 5, which is the topology generated by all intervals of this form. That means this type of sets form a basis for this topology. And I write just this sentence. It's easy to see that K5 is the set of all non-negative real numbers. But how is it easy? Let's now elaborate. You look at this diagram where you can see the real line. The only thing is that now the topology is tau 5, not the standard topology. Let's now concentrate on any positive real number x. It will obviously lie to the right of 0. Now, what makes this x an element in the closure of K, that is an element in K5? Well, for that to happen, this should be the case. If you choose an arbitrary basis element in this topology that contains x, then that basis element should also intersect our set of reciprocals of positive integers. Any such basis element will be a ray like this, okay, which say starts at a point and moves leftward. But because such a ray has to contain x, so the right end point of the ray has to lie to the right of x, and at the same time this side is open, okay. So you cannot take x itself as that A. It should be to the right of x. Now this ray contains x inside of it, alright. Does this ray also contain those reciprocals, at least one of them, of positive integers? Yes, they are here somewhere. But you have to be careful about all the possibilities, okay. It seems as though this x is very far away from 0 and all the reciprocals of positive integers lie to the left of x. That's not necessary. X can actually be very close to 0. Who knows? X is just a positive real number. It can be close to 0, it can be far away from 0, anything can happen. But no matter what the situation is, no matter how close x is to 0, you will still find reciprocals to the left of x. And that is why any such ray which contains x should also contain at least one reciprocal, actually infinitely many of them. But why is that the case? That is because the reciprocals of positive integers converge to 0. Okay, converge to 0 in the sense that converge to 0 in the ordinary standard topology. This means that no matter how close you take your x to this 0, still you will continue to find reciprocals which are closer to 0 than x is. That is why such a point x will belong to K5. That means all positive real numbers will belong to K5. So that leaves us only with 0. Why should 0 also belong to K5? An exactly similar argument works for 0 as well. So now our point of attention is 0 itself, and you have considered any basis element containing 0, which is again a ray of that type. For such a ray to contain 0, this right boundary point A itself has to be a positive real number. Because this side is open, it cannot be 0 itself. And that is why in this case also, no matter how close this right boundary is to 0, there will be actually infinitely many, almost all reciprocals of positive integers inside this ray. So that's why 0 also belongs to this. However, the fact that we are claiming K5 is this tells us that we now also have to check that negative real numbers, none of them belongs to K5. How is that true? Say x is any negative real number, so now it will lie to the left of 0. It can be close to 0 or far away from 0, but it lies to the left of 0. Now you can think of a real number which lies between x and 0. Because x is negative, x is not equal to 0. Okay, so there is some region between 0 and x, and you can choose a real number a inside that region so that it lies somewhere in between. It is neither 0 nor x. And then you consider this ray with that real number as the right boundary point. That ray of course would contain x, but this time this ray has no such reciprocals of positive integers. And that is why you have found a neighborhood of this negative real number x in the topology tau 5, which does not intersect the set K. And that is why x does not belong to the closure of K in this topology. So that's why this side is missing from the closure. So the closure should be this. And then part B, which of those topologies satisfy the Hausdorff axiom and also T1 axiom. That means these two are different. Which one of them satisfies which one of these two? You may also encounter a topology satisfying both of them or none of them. We start the solution like this. We know that the standard topology tau 1 is Hausdorff. Obviously, in the standard topology, you can separate two distinct points. Points means two distinct real numbers using disjoint neighborhoods. And that is why it is T1 as well. Any Hausdorff topology is automatically T1, as we saw in the section. Since tau 1 is contained in tau 2, that is the K topology is finer than the standard topology. Strictly finer actually, but we don't need that fact here. That is why tau 2 is also Hausdorff and hence T1. How exactly? Well, what does tau 1 being Hausdorff mean? It means that if you choose any two distinct real numbers, then there will be disjoint neighborhoods which are elements in tau 1 of those real numbers. But because of this containment, those disjoint neighborhoods are in tau 2 also. So that is why tau 2 is also Hausdorff, and that is why T1 as well. The finite complement topology tau 3 is T1 but not Hausdorff. It's not very difficult to see why. Actually, we have already discussed this. I mean, we mentioned this, we did not elaborate why, but it's very easy to see. You just recall the definition of finite complement topology and you try to think of what the open sets are. Okay. And from that definition itself, you will find that the topology is T1. Every one-point set will be closed. But at the same time, it will not be Hausdorff because no two non-empty open sets are disjoint. Okay, any two non-empty open sets will intersect each other. That's why it's not Hausdorff. The upper limit topology tau 4 is Hausdorff and hence T1. It's pretty easy to see why this is Hausdorff. I mean, you can directly get disjoint neighborhoods for distinct points. And for neighborhoods, you can actually choose basis elements, those half-open intervals. And finally, for the topology tau 5, we've considered the complement of the one-point set 0 in R, which of course is the union of these two rays, the left half ray and the right half ray. This set, however, is not in tau 5. That means this is not an open set in this topology. What does it mean? It means that this singleton set is not closed in this topology. And that is why tau 5 is not T1. Because Hausdorff-ness implies T1-ness. So lack of T1-ness implies lack of Hausdorff-ness. So it's not Hausdorff either. However, it's not immediately clear why this is not open in tau 5. Let's see why. And for that we again draw one such diagram. Suppose forcefully that this is open. What is this set geometrically? It's the entire real line from which 0 has been removed. Alright, so that single point has been removed. Now we are supposing that this is open. What does it mean? It means, among other things, that if you choose an arbitrary point from the set, then there exists a basis element in the topology which will contain that point and will itself be contained entirely inside this open set. Open set means we are supposing that it's open, for which this should happen. Say you consider a positive real number that is in this set, right? A positive real number is not 0. Okay, it lies to the right of 0. And consider a basis element in the topology tau 5, which will be a neighborhood of this x. But in tau 5, the basis elements are raised like this. So for them to contain x, the right end should lie to the right of x. Say that right end is A. But then is this ray entirely contained in this? No. 0 is causing a problem. And that is why our supposition that this is open is actually wrong. So this is not open in tau 5 in spite of how it looks. We are familiar with the standard topology the most. That's why the moment you see something like this, you think that it's open, but be careful. The topology is not the standard topology anymore. So that's the reason.